Now we saw the effect of downsamplers and upsamplers in the time domain. A natural question that arises is, what are the spectral effects? What is the frequency domain effect of doing downsampling and upsampling, right? So let us try to investigate into the frequency domain effects of the decimator first. Now we start with y suffix d of z, d standing for the decimator. We take the z transform of the signal, which is yd of n z power minus n, and we just drop in the equation for, or I would say the relationship between x of n and yd of n, and yd of n is basically x of m times n. So this is what we have, right. Now this is not enough for us to proceed. So let us define a sequence x1 of n equals x of n when n is a multiple of m and 0 otherwise. Now I define x1 of n as x of n when n is a multiple of m and 0 otherwise, so that I can accommodate, because there are holes, right. I mean at these points mn it exists, at other points it does not. So but to take care of those holes, we just define this new sequence x1n as follows. Now we can plug this into this equation, y the output of the decimator, y I mean the frequency domain, the transform of this the output of the decimator yd of n is basically y suffix d of z, which is summa n equals minus infinity to plus infinity x1 of m times n times z power minus n. So this is basically we are fixing those holes at points where they were not multiples of n. And if I let m times n equals k, right, the usual trick that we do, I can say this is x1 of k where my k equals m times n z power minus k upon m. If I let this happen, then this is from k equals minus infinity to plus infinity x1 of k times z power minus k upon m. Okay. But I am not sort of still complete, because I now have to relate x1 of n with x of n. I have just written this in this clause, x1 of n is x of n, n is a multiple of m, 0 else. So I have to kind of put this into some compact form than an if else statement like this, right. So for this we go one step forward and we say x1 of n equals some Coombe sequence times x of n. This Coombe is literally like your like your comb, the hair comb, where Cm of n is 1 if n is a multiple of m and this is 0 otherwise. So, we have gone a little one step forward, right. This is Cm of n is 1 when n is a multiple of m, 0 else. Still it is like an if else statement, we think it is not simplifying, but here is an important relationship between the exact definition of this comb sequence and this comb sequence can be written in this form. Which links the mth roots of unity as follows, right. C suffix m of n links the mth roots of unity as follows, given by this relationship. It is not too difficult for you to see, because when n is an integer multiple of capital M, right, this is going to be the 0, I mean when n is 0 or m, 2m, 3m, so on and so forth, right. When it is integer multiple of m, this term becomes 1. So, basically you are adding 1 1 1 1 m such copies, and this is basically m by m upon m is basically 1, and if it is not an integer multiple of m, we are basically summing the roots of unity, and summation of the roots of unity is 0. Why? Basically if you think about this equation z power say m minus 1, right, this equation is z minus say omega naught z minus omega 1 dot 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 z minus omega m minus 1, we have m roots here. Now observe the coefficient of the m minus 1 term, it is 0, but sum of the roots are basically the coefficient of the monomial z power m minus 1 in this product, right. So therefore this has to be 0. So therefore the comb sequence is linked to the roots of unity according to this formula. Now since this is very clear and interesting to us, so now we can say x1 of z is 1 upon m summa k equals 0 to m minus 1 summa n equals minus infinity to plus infinity x of n omega power minus k n. So I am just removing this index m in this root, it is implied z power minus n. So just an aside that coefficient of z power m minus 1 is 0, and summation on the roots of unity is 0. This is just a proof aside. Okay. Now x1 of z is linked with x of n using this relationship. So what I have done is nothing, I am just now taking the z transform here. So this x of n z power minus n is whatever I have in the original z transform, right, and this Coombe sequence is just being replaced by this formula, nothing special. So if you went in the if else statement saying n is a multiple of m, this exists, otherwise it is 0, then you would never have simplified. Since we wanted to fill in the gaps for to account for the zeros when n is not a multiple of m, we had to introduce the Coombe sequence and link the Coombe sequence with the roots of unity, and that is a trick, and you will see this trick in number theory as well. In various other properties in number theory, you will see this trick. So it is a good trick to have this at the back of your mind, right. Now we can simplify this further. This is 1 upon m summation k equals 0 to m minus 1 summation n equals minus infinity to plus infinity x of n times z omega power k times power z omega power k power minus n. It is just routine algebra, and then if you sort of just interpret this equation here, right, this is basically x of z omega power k. If x of z corresponds to x of n, x of n, the z transform of this is basically x of z omega power k, right. Now we are sort of ready to put this in final form. We say yd of z is 1 upon m sum k equals 0 to m minus 1 x of z power 1 upon m omega power k. Why? Because yd of z is x1 of z power 1 upon m. Just go back here and just look at this equation. Yd of z is x1 of z power 1 upon m. We will see this 1 upon m here, right, because of this relationship. We are ready to see how the output of the decimator looks in the frequency domain, right. This is the formula, this is the derivation for the frequency domain effect of the downsampler. Okay, I just have removed this subscript capital M from this derivation, but you can, it is implied that it is there. Now let us work back what it is in the Fourier domain. So if I look at yd of ej omega, it is 1 upon m summation k equals 0 to m minus 1 x of, now we have to be careful here. So the mth root of unity omega m, again for for you to recall is e power minus j 2 pi by 2 pi by m, right. And so this is x of j x of e power j times omega minus 2 pi k upon m. So this is what we get for the response of the decimator in the frequency domain. Now what is happening here? Just observe this equation here, right. So now this omega minus 2 pi k for k equals 0, 1, 2 so on till m minus 1, you can interpret this as basically a translation of your spectrum, and this m basically scales the spectrum, right. And what is happening is you are basically stretching it in the frequency domain. Whatever is compressing in time because of slashing of the rate is basically stretching in the frequency domain, and basically for every such copy you are evaluating this spectrum and you are summing it up, and your amplitude is basically scaled by 1 upon m. So there are 4 different operations that are happening. One, you stretch x of e j omega by a factor m to obtain x of e j omega upon m, right. I mean the m is in the exponent. Then we create copies, that is m minus 1 copies of this stretched signal. So basically we stretch it, take m minus 1 copies of the stretched signal by shifting it uniformly in successions of 2 pi, then we add the shifted versions to the unshifted stretched version. Last we scale by a factor of m. Well, this is a scale down by m, which is basically you multiply by a factor of 1 upon m. Okay. Okay, so there are 4 different operations happening, and you have to realize that the stretched version, that is x of e j omega upon m, is itself not 2 pi periodic, but after adding these shifted versions it is 2 pi periodic. So it is good to imagine how this spectrum really looks like. My figure is not perfectly up to scale, but I think you can still follow this up. 0 here, just have pi, I just have 2 pi, pi here, 2 pi, say 3 pi, say minus pi, minus 2 pi, minus 3 pi, dot dot dot. So let us say we have our original spectrum xej omega, and let us say it is periodic. So on and so forth. Now if you downsample this by 2, what happens is this base spectrum stretches by 2 and you will have copies of that, right. So basically I start with this diagram here, right. That means I have to now stretch this thing out from pi, it moves to 2 pi, this point moves somewhere here, right, and this is going to be and then similarly you will have one more copy of this signal like this, and since it is periodic, you know you can think about these stretch versions on either side of the origin, right. So this is basically the frequency domain effect of the decimator. So I have forgotten a scale factor of half. You just have to bring this half as well to say that you have this, basically you're doing some translations and basically you're folding this. Now similar to the decimator, we have the expansion phase as well, and let us derive the frequency domain analysis of the expansion process. Now ye of z is sigma n equals minus infinity to plus infinity. Basically I take the z transform of the output of the expander, and this is basically, so I said this y of n can be written as this summation being valid when n is a multiple of L. So I have ye of n, expansion of n, of expansion of the expansion process, right, of x of n, and I introduce a subscript, I introduce a variable k which is going from minus infinity to plus infinity, and n is basically an integer multiple of L. So this is basically ye of k times L z power minus k times L, because n is a multiple of L, right, and therefore I bring that variable k into picture, and now this is very easy for us to simplify, because we do not now have a hole here, unlike the decimator where we had this if else clause, right, something for a multiple of n, 0 otherwise. We here now do not have any such thing here because it is sort of clean, and you can just say this is basically k equals minus infinity to plus infinity, ye of kl is now x of k z power minus kl, right, because ye of n is x of k upon n, that is what we had. So, therefore, y of k l is basically x of k, and now this is easy for us, and this is x of z power l. So, there we had something z of z power 1 upon m for an M4 decimator, and here if we observe it is e power l. So, if we are increasing the sampling rate through this expansion process, right, you can imagine that the spectral effect is basically shrinking due to just sort of a dual due to duality, right. So, let us see through this with an example. Pi to pi, 2 pi, 3 pi, dot dot dot. So, let us suppose that we have the same spectrum we started off with. So on, and let us say it is periodic. Suppose I consider an L equals 5 upsampling, right. So, now this is going to be slashed, or it is going to be compressed in the frequency domain, and we have this is a 1 over 5 factor stretch, sort of a compression in the frequency domain, but since it is a periodic signal, right, we can think about having copies at 2 pi by 5, so on and so forth. Otherwise, there are no copies, you just have to have one, you will have just one copy here, unlike the decimator. Since this is, we are assuming some periodicity here, therefore, we can think about that we will have multiple copies, right. So, you just have to focus upon just this. Now, the problem, if the spectrum is periodic, as you can imagine, is the compressed spectrum. If the original spectrum is 2 pi periodic, the compressed spectrum has many images, and these images are basically ghosts, right, and this causes this imaging effect, and if you have to be careful, you really have to filter out these images through a filter. That means you can put a filter which cut off at pi by 5 here, modulus omega is less than pi by 5, just have a sharp cut off at pi by 5, sharp or gradual, we'll discuss these issues, but you will have to have a filter which cuts off and gets just this image, one image out, and then you do what you want with it, okay. So, this sort of completes this module or this lecture, part of this module in multi-rate. So, we'll stop here.